All right, average rate of change. Or I call it in short AROC. If you're looking at a generic function whose graph is the following sketch on the XY coordinate system, for instance, you have a function that behaves in this manner. So this is y equal f of x, and you're interested to know what is the change that took place between x equal a and let's say x equals b right here on this interval. Well, if this function was a linear equation, then the graph would be a line, and the rate of change will be simply the slope of the line. Well, this is not a line; it's a curve, and here the slope or the rate of change is different. Well, the rate of change is basically your is what we call a difference quotient. Is the difference in output divided by the difference in input, or you know it more as rise over run, the difference in the y value divided by the difference in the x value. Again, the slope of a line. Except again, we don't have a line. So if we move from A to this point, let's say x1, I have a certain change, which is the slope. But if I move, for instance, from this point, which I call x2, to B, I see that the curve is steeper. So the change, the delta y over delta x, will have a greater value between x2 and B than A and x1. So we are talking about varying rate of change. And therefore, we need to take the average. And if we are interested to know what happened between A and B, we need to take the average. How we do so? We're going to draw a line that intersects the 2 points in question, and a line that passes through these 2 points, like so. Okay, the points in question have the following coordinate. This point has an x value of A and a y value of f of A, and this point right here will have an x value of B and a y value of f of B. Okay? And we're going to say that the average rate of change will be the slope of this line. Well, this line intersects the curve at 2 points. We call it the secant line. So this line is the secant line. Now, some of you took trig and heard the term secant, and secant is a trigonometric function. It's the reciprocal of the cosine. The secant is hypotenuse over adjacent, if you remember, if you know that. So this is not the same as the trigonometric function secant. However, they related. But for our discussion, when we say secant, we are talking about the line that is intersecting the curve at 2 points. So let's write something about the secant line. And when we are talking about the secant line, we are talking about the secant line between 2 points. So a secant line is a line that intersects a curve at 2 points. what is the average rate of change? Well, the average rate of change, or the AROC, and here we're going to define the average rate of change on a certain interval. It will be the closed interval, and the interval in this case will be the interval from A to B. So we'll use the bracket notation. So we're going to say the average rate of change on the closed interval AB is the slope of the secant. The slope of the secant line. And of course the secant line through, because we are passing through these 2 points, A, F of A, and B, F of B, like so. Okay? What is the slope of the line passing through 2 points? Well, it's rise over run. So let's see, what is the rise as we go from x equal A to x equal B? Well, this is F of A, and this is F of B, and this length right there is the rise. So this is the rise, or F of B minus F of A. Okay? Same thing, the difference between B and A is the run, or the quantity B minus A. And we're looking at the rate of change as the ratio between the rise and the run. So we're going to say that the average rate of change as we move from A to B, notice the notation, will be the rise, which is F of B minus F of A, divided by the run, which is B minus A. This is something that you have seen in college algebra. I hope so. And this thing is called, this type of ratio, because I have a difference on top and I have a difference on the bottom, we call it difference quotient. Again, a term that should be in your college algebra curriculum. Now, I want to take you a little bit farther forward, because so far I think this is all something that you've seen before. What happens if we want to find out the rate of change instead of over an interval, let's say from A to B, I want to find out the rate of change at exactly A, or at exactly B, or at exactly x1, or at exactly x2, or at exactly any given point. Well, say I want to find out what is the rate of change at A. Obviously, the estimating the average rate of change from A to B won't be a good estimate. What I can get a better estimate if I go from A to another point x2. I can improve this estimate if I go from A to another point x1. And I can get even a better estimate if I go from point A just a little bit to A plus a little quantity. So as we narrow the interval, as the interval becomes smaller and smaller, we have a better estimate of the rate, the rate of change at a point. We call this the instantaneous rate of change. The instantaneous rate of change. And this is the focus of calculus. What the calculus was trying to figure out is ways to calculate the instantaneous rate of change. So let's write a comment here. Even though we're going to focus today on the average rate of change, in preparation for calculus, I'd like to introduce you to the instantaneous rate of change. So instantaneous rate of change Instantaneous, I think I have an extra T here. And long term, so I'm going to, long name, so I'm going to shorten it by using the acronym AROC. Okay? So what is the instantaneous rate of change? Let's first visualize it. I'll draw another sketch where I have a curve, y equal f of x. Okay, so here's a generic curve, y equal f of x. And let's say I want to know what is the instantaneous rate of change, let's say at this point right there, where x equals a. So what happens is, if I move the second point closer and closer and closer, then I'll have the rate of change at this point where the coordinates are a and f of a, like so. And turn out that the line that represent the line whose slope represent the instantaneous rate of change, do you know how we call this line? It's a tangent line. Again, tangent is a trigonometric function, and they are related, but in our context, when we say tangent, we mean the tangent line. And you can tell the difference between secant and the tangent, even though the following, what I'm about to say, is not a definition of the tangent, but in layman term, we're going to say that a tangent at a point is the line that just touches the point. Okay? The exact definition will be the line that touches a point and is perpendicular to the radius of the curvature. But that's next semester. For our intended purposes, the instantaneous rate of change is the slope of the tangent, and the tangent just touches the point at touches the curve at one point. Okay, so do you need another second or two to write down, to finish writing down this page? No? So let me write the following here. So a tangent line, again, this is a layman term. It's not a definition. Touches, and here I'll put in parentheses locally, and I'll explain in a minute why I include the word locally. So locally touches locally a curve at one point. Okay, so that kind of layman description of the tangent, and now we're going to say that the AROC, the instantaneous rate of change, is the slope of the tangent line. So the AROC at, I should exclude, I should say at x equals a, like so, because we're talking about a tangent at a point, not in general, is the slope of the tangent to the curve at x equal a. Okay? Now, some of you took introductory to calculus in high school, and I learned that the slope of the tangent is also called Okay, the slope of the tangent or the AROC at x equal a is also called, and what shall I put in? Call it out. Anybody know what's coming next? Think calculus. How do we call this in calculus? Very good. It's the first derivative. You said so? The first derivative is called the first derivative and we'll say of a function f of x, and I'm not writing it down, but of course the curve is the graph of f of x. Actually, I just changed my mind. I'll write it for sake of completion, where the curve is the graph of f of x. So now I've completed this statement. The last thing that I need to say is something about why this exclusion locally. Why did I include the word locally? Well, to demonstrate the reason why, let me draw an example here. Again, some curve on the xy on the xy coordinate system, but this curve looks like that. Okay, so this is y equal f of x, and the point in question is right here. This is x equal a. And what happened here is the following. The tangent is right here. Okay, so you see that locally it touches at one point, but there is another point, let's say point C, where it intersects. That's why I said it touches locally. So right at x equal a, it is a tangent, but it's also a secant if you look at C from C to A. Okay, so let's write here a remark. Note that the red line is both a tangent and a secant. So locally it's a tangent, but on an interval, on a greater interval, then it becomes a secant because it may intersect the line.